38, problem 38 in 14.2. Looks pretty good. It wants the volume between two surfaces. You know, we've been doing, all this volume we've been doing it's usually a surface, and then we've been finding the volume under that surface down to what I call the floor, or the XY plane. You know, so the XY plane has been our bottom, and the surface has been our top. But this one says volume between two surfaces, so that's okay. But I wonder what you think you know how you set up an integral for this? I mean, nobody taught you how to set up an integral for this. I mean, normally it's a double integral of a surface over a region R. I mean, that's how we get volume. But if I'm doing it between two surfaces, do you have a thought? Do you have a thought? By the way, for 38, the two surfaces are z equals x squared plus y squared, and z equals 18 minus x squared minus y squared. And I can try to draw a picture of this for you, but that's the tough part. Drawing these 3D pictures is kind of tough. But if I'm trying to find the volume between two surfaces, I think I got an upper surface and a lower surface. Any ideas?
Compare the two surfaces. Dx,
right, so,
dy switch.
So this integral will give me volume, and the way I've described it is it's the volume under the surface down to the xy plane, the flat x. So it's just automatically down to the xy. You know, the analogy is back to Cal 1. The first thing you did in Cal 1 is you would do some integrals, and somebody would tell you, oh, what you're doing is the area under a curve. But by default, automatically, it was always the area under the curve down to the x-axis. And when someone finally introduced, what if you want to do the area between two curves? And then what did we do? Do you remember?
Top minus bottom.
Thank you. We would do top minus bottom to get the area between the two curves. Well, that's the analogy here then. That's the analogy here. I mean, this normal, what we've been doing a lot of is the volume under a surface down to the xy plane. But if I've got two surfaces, I probably ought to subtract them. I probably got a top and a bottom, right? A top and a bottom surface, and I should subtract them. What goes in here is the subtraction of the two surfaces, right? So, who's on top and who's on bottom? Shut up, Max. So, let's see. I would say that you have this paraboloid here. That's what this guy is. This z equals x squared plus y squared. That's the paraboloid. And it sits at the origin and it opens up, and so I'm sort of thinking that's the bottom surface. You know, I know what this other one is. It looks real familiar. I've run into them a few times. He's an upside down version of this paraboloid. He's an upside down version of this paraboloid, actually pushed up 18. He's pushed up 18, and he's an upside down version of this kind of paraboloid. So now where they intersect, that might be interesting and might be important, but at least now I think I figured out who's on top and who's on bottom. I think I'm going to set up a double integral, and I think this one's on top. 18 minus x squared minus y squared, and I'm going to subtract the one that's on the bottom, which is this surface, x squared plus z plus y squared. I'm sorry. It's like that function minus that function, or that z minus that z. That's how I'm setting it up. So that's part of the battle, is setting up your integral and what's the integrand and who are you going to integrate, how are you going to integrate that. We can clean that up a little. But then the other battle is setting up the bounds. And so you got to worry about dy dx or dx dy, and then you got to set up the bounds for that. And that's all dictated by the region over which you're integrating. And the region over which you're integrating is not 3D. The region over which you're integrating is a 2D region in the xy plane. Although on this problem, that sort of confuses me. Look, what is the region in the xy plane?
What's that little?
Looks like a dot. I mean, there is no region in the XY plane, but maybe you understand that what it is
There's a circle.
it's sort of the shadow
Yeah.
of, it's the region in the XY plane is the shadow of this shape in the XY plane. And I think the shadow of this shape in the XY plane would be the widest and the biggest sort of at this intersection. I think these are two paraboloids that intersect. And I think that the shadow of this in the XY plane is the region we're talking about. So now I'm curious where those guys intersect and what that might look like. Or how would you investigate where they intersect?
Set them equal to each other.
Yeah, set this Z equal to this Z. I'm going to set them equal to each other and investigate where they intersect. Right, let's check this out. These guys intersect. That's when x squared plus y squared equals 18 minus x squared minus y squared. Okay. Hey, if I add that x squared and y squared over there, I got 2x squared, and 2y squared equals 18. If I divide by 2, x squared plus y squared equals 9. That is sweet. You know what that is, right?
What's your number on the football team?
It ain't a number. Idiot. No, it's, again, thank you, a circle of radius 3. Right. It's a circle of radius 3. You know, again, that's a circle of radius 3. That's not, there is not a picture of a circle of radius 3 in the XY plane. This circle of radius 3 is where they intersect, which is occurring up here somewhere at some Z value. I guess, hang on, what Z value would that happen? If Z was a 9, I guess if Z was 9, you'd have a circle of radius 3. So it must be happening right here at Z equals 9 is where this intersection is happening. And at that place, that's what the shape is. And then like I said though, so it's not in the XY plane, but I want to look at the shadow of it in the, I want to pretend it's in the XY plane. The region over which I'm integrating is that region, a circle of radius 3 in the XY plane. Right. Right. All right, well, see, here's where, all right, here we go. Do you want to do it dy dx or dx dy? If it's a circle of radius 3, it hardly matters. Right. Here, we'll do dy dx. So that means I have to let y go first, which means I probably should solve this. I mean, here's the equation of this thing, but I probably should solve for y in terms of x. What a pain. If you solve for y in terms of x, not that much of a pain, but you do get this plus and minus square root of 9 minus x squared. And the positive square root is the top semicircle, and the negative square root is the bottom semicircle. You guys know that, right? Mm-hmm. Negative square root of 9 minus x squared is the bottom semicircle, and the top semicircle is the positive square root of 9 minus x squared. So I think y goes from, I mean, I need like, maybe I need a little y stick. My y goes from that lower semicircle to that upper semicircle. I think that for my bounds for y would be that. Negative square root of 9 minus x squared, positive square root of 9 minus x squared. And then my bounds for x can be a little more broad. And by the way, I don't want them to have functions. And when I get to this last set of bounds, they need to be numbers. And so I just want the furthest left and the furthest right number for x. It's easy, please.
Negative 3 to 3.
Negative 3 to 3. Right, you guys? After you do y, then x is going to take that rectangle that way, negative 3 to 3. Dude, we got it. We got this set up. We get the volume of between these two surfaces. That's kind of a good problem, man. It's almost like perfect. Easter's coming up. It kind of looks like a Easter egg. Two paraboloids. That's interesting. doing this problem is probably horrible. Doing this, I mean, just setting it up was not bad, really. That wasn't too bad, but it takes a lot of thought, as you can tell. And a lot of my questions, to save a little time, a lot of my questions might be, please set up the integral. And you don't really even have to do it. Your homework is full of doing the integrals. You got to do them. And you should practice doing them to get the volume. But to do this one in rectangular coordinates, like it's sitting in x's and y's in rectangular coordinates, and it's in 14.2, where they kind of want me to work in rectangular coordinates.
Hey, can you just take the 18 minus x squared minus y squared and subtract that and just keep it like that?
I'm going to clean this up. Yes, sir. Before you integrate, you should clean this up a little bit. What is it? It's an 18 minus 2x squared minus 2y squared, I think, when you distribute him. So you're right. I end up integrating this, dy dx. These are my bounds. But I'm about to tell you that I don't want to do that. I do not want to do this problem in rectangular coordinates. It's going to suck with these nasty square root bounds. And so what we barely learned the other day, and we'll learn it more today, because I'm about to do this in polar. I would rather do this in polar. And what's the big thing that makes me say I should do this in polar?
Circle.
The circular region. The region over which I'm integrating is a circle. That's the main thing that tells me I should do it in polar. Also, the thing I'm integrating has some x squareds and y squareds, which convert nicely into polar. But that's that's not the main dictating thing. The main thing that makes me switch to polar is these are nasty bounds for a circle. And in polar coordinates, they would be beautiful bounds for a circle. So, I'm abandoning 14.238, and I'm pretending, I'm going to just pretend I've learned about polar coordinates. I'm going to switch the whole thing to polar. So, I'm going to switch the whole problem into polar. Switch to polar. All right, so watch what happens. Switch to polar means the actual function, which we did simplify right here, has to get switched into polar. Any clues how to do that, you guys? How to switch him into polar? We wrote down a lot of polar equations the other day.
18 minus 2r squared.
Good. You might have just said it correctly. Let me think here now. One of the main things, here's some polar equations. We came up with x squared plus y squared is r squared. That's awesome. Also, x equals r cos theta and y equals r sine theta. These also might help with sometimes. So you can, in fact, anytime you see an x, you can replace it with r cos theta. Anytime you see a y, you can replace it with r sine theta. But the truth is, if you cleaned all that up, what you would discover is what he just said. What did he say? If you factor out a 2, if you factor a negative 2 out of that, you got x squared plus y squared. So what's x squared plus y squared? R squared. So awesome. The integrand just turned into 18 minus 2r squared. We're converting it into polar, and that's part of the game. Convert the integrand into polar. Hey, what about the dy dx out here on the end? The dy dx gets converted into polar.
dr theta.
It is dr d theta, but I told you the other day, and you better remember this, it comes with this extra little r. So it's r dr d theta. Imagine a Neanderthal pirate. R dr d theta. R dr d theta. You know what I'm saying? It comes with it. It's part of the dA. This extra little r comes with it. It's part of the dA. I haven't explained it real well. Just believe me for now. Hey, it comes with it and it's part of the dA, but then immediately you sort of join it, or whenever you start to integrate, you join it up with this crap. It becomes part of what you integrate. It becomes part of the integrand. What?
Nothing.
Okay, so I converted the function. The integrand got converted to polar. The little dA got converted to polar. And now I want my bounds converted to polar. But I don't sit here and convert these bounds. What I usually do is I go think about my region. And I think about my region in polar coordinates. And there it is. It's a circle of radius 3. Here, let me just blow it up a little bit for you. It's a circle of radius 3. And in polar coordinates, what is the name of that circle of radius 3?
R3.
R equals 3. We stumbled on that idea the other day. If you're a circle of radius 3 centered at the origin, your equation is R equals 3. Now, if you're trying to sweep out this region, then R, listen, we've been talking about how Y moves vertically, X moves horizontally, but R moves from the pole out. R moves differently. R moves like R moves, from the origin out. And if you drew that R there, I think your bounds for R would be
0 to 3.
0 to 3. What if you drew it over here? 0 to 3. What if you drew it over 0 to 3? I mean, I think your bounds for R are 0 to 3. So easy, so cool. Wade, that's how you do circles. You switch to polar. You don't do this. If you got a choice, you switch to polar and integrate over this circular region using polar coordinates. Hey, what about theta? Can you tell me the bounds for theta? Please?
0 to 2 pi.
2 pi.
Theta
0 to 2
is,
pi.
you know what theta is? So I got R going from 0 to 3. Now to sweep out the whole damn circle, theta should go from
0 to 2 pi.
0 to 2 pi. Yeah. Hey, if we were just doing the top half of the top semicircle, I think theta would be 0 to pi.
Yeah.
But we want to go all the way around, 0 to 2 pi. This is the same integral. Well, it's not do that integral and you'll get the same answer as if you did this integral. This is in rectangular coordinates. It'll take a page or 2 or 3 pages, and this will take 5 seconds.
R.
Yes, sir.
Can we do 33?
Maybe. You guys want to, let's finish this one. Like I said, it takes 5 seconds. We'll see if that's true. Distribute the R. It's 18R minus 2R cubed. And then you are going to integrate with respect to R. So here we go. Now we should integrate. R squared divided by 2. R squared. 9R squared. R to the 4th divided by 4. R to the 4th. Evaluate from 0 to 3. Plug in your 3. That's 9 times 9. It's 81 minus 81 halves, I think. Plug in your zeros, and those are all zeros. I think 81 minus 81 halves is 81 halves. So the answer to the inner integral is 81 halves. We still have to integrate with respect to theta from 0 to 2 pi. This part's real easy. You're integrating a number with respect to theta. It is 81 halves theta. You're going to plug in your 0 and 2 pi, and this was my number on the high school. Here it is. When you plug in 2 pi, 81 pi. Yep. Defensive end for the Chicago Bears. 81 pi. That's the volume between these two things. That's awesome, man. It's like my egg. Yep, my Easter egg, sort of.
Sounds delicious.
Yep. That's the volume, right? It's like one of them Cadbury eggs or whatever you call those things. Calculate the calories or whatever. That was fun. You guys got any questions?
Oh, 33.
You said 33. Nothing on here. You guys happy with this? It's a pretty good problem. I hadn't done any volume between two surfaces. We had to come up with the idea of subtracting the two surfaces. We had to come up with that idea. But no big deal. And then we just had a lot of work. It's a lot of little nitty-gritty work. Nothing really that hard, but a lot of little just details to focus on and pay attention to. But once you convert it into polar, then it's easy. I'm not going to make you do this. I'm not going to make you do this. I'm not going to make you you do that. Hey, I'm going to get to his question. If you see an x squared plus a y squared, you just go ahead and call it an r squared when you're doing converting, I guess. I mean, it's easy. If you see an x squared plus y squared, call it an r squared. But watch this, just in case you forgot that, and you decided to do this. X is an r cos theta, and y is an r sine theta. So if you chose to do this instead, well, right, watch what you get. You get r squared cos squared plus r squared sine squared. You should factor out the r squared, and you're left with a multiplied 1. Thank you. So anyway, it turns into r squared the long way or the short way, right? It's r squared. Okay, let's see what he said. He said something about 33. You're in 14.2, huh? In 14.2, 33. Yeah, so that has a nice picture, and it's got the volume between two surfaces, I guess. This is kind of funny. They got this plane slicing through a paraboloid. They got a nice picture. I can't draw a picture that well, I don't think. I don't know if I have to, but they got a nice upside down paraboloid. But then they have so it's kind of a bulging paraboloid, but then they have this plane. This plane is actually looks like it's touching there and there. So it looks like there's a plane. Holy shit. Bad, but there's a plane slicing there, and so you get this. You kind of get this. You sort of get this bulging little shape right here on the side of that damn paraboloid. The plane's cutting off a slice of that paraboloid in a way. And that's the volume that they want, and the book has a better picture. So this is 33, but it does fall in this category of a volume between two surfaces again. Let's just hang on a second. If I point to the plane, they called that plane z equals 4 minus 2x. Sorry. The plane is z equals 4 minus 2x. The paraboloid is z equals... It's an upside down paraboloid. They called it 4 minus x squared minus y squared. 4 minus x squared minus y squared. All right, well, I think I want to set up a double integral with sort of a top surface minus a bottom surface again. So here I am. I want to just set up this subtraction in here, you guys. Who do you think's the top surface and the bottom surface? I mean, the plane slices through the paraboloid, so the paraboloid's bulge it's on top. So the paraboloid's on top, and we're subtracting the plane. So the paraboloid, it's this z, which is the paraboloid, minus this z, which is the plane. And now I got to work on dy dx or dx dy, and then my bounds, and that's all dictated. I swear to God, the rest of this problem, I only drew that to help me figure out what I'm integrating. The rest of this problem is all dictated by the region over which I'm integrating. That's the key. That's the thing students don't get sometimes. You got to get now you got to analyze the shadow down here, the region over which you're integrating, which I can sort of imagine is something, like that. Maybe it would be best to set them equal to each other again and see where they intersect. See what that intersection looks like. I think I'll do that. I'm going to set this z equal to look at their intersection. And then what I'm really looking at is the shadow of their intersection down in the xy plane, but where this z equals this z. Oh, dude, that ain't too bad. the 4's cancel. Hey, the 4's cancel, and then if you don't mind, I'm going to multiply by a negative. If I multiply by a negative, I get that. Okay, life's getting tougher all of a sudden. In order to sketch this, I know what it is, but I got experience. Maybe you know what it is. I mean, in order to sketch it, though, I got to play a little algebra game. I want to complete the square. I want to see what this looks like. I'm going to move, watch. I'm going to move the 2x over here like this. I'm going to leave a space, and I'm going to complete the square. I'm going to add the perfect number right here. What is the perfect number I should add? 1. It's half of this number squared, so I'm going to add a 1. If I'm going to add a 1, I should go over here and add a 1. Now I have an x minus 1 squared plus y squared equals 1. Now that's pretty famous. That is a circle. The center of this circle is what?
1, 0.
1, 0. Good job. On the x and y, it's a circle in the xy plane. It's got a radius of 1. It's centered on the x-axis at 1, 0, but it's got a radius of 1. That's the shadow over which I'm integrating right here. That's this right here. When I drew it a little more elliptical. It looked kind of elliptical here in my picture, but by the time you cast that shadow down there, it must be a circle of radius 1 sitting there. By the way, this must have been a 2 right here where this touches. You guys okay? That was kind of quick. Maybe I was trying to find where they intersect. I just messed, this is the equation, and I just knew what to do with that equation, and you will too. Move the 2x over, complete the square, and then you can see what it is. It's just an off-centered circle. Well, it's a circle. If it's a circular region, I would like to do polar. I'm not supposed to know how to do polar in 14.2, number 33. I'm not supposed to know how to do polar. Let's just pretend I don't know how to do polar. If I'm setting this up with respect to y and x, I'm going to let y go first, I guess. That means what? That means I got to solve for y. I kind of got to solve for y, right, you guys? Because I got to go from the lower semicircle to the upper semicircle. And that means I should solve this for y, or, hey, I can solve this for y. These are the same equations. I think I'll try solving this for y. Move the x squared over, take the square root. I think y is plus or minus the square root of 2x minus x squared. Are you guys okay with that? Here's the other version of it is this. Plus or minus the square root of 1 minus the x minus 1 squared. Doesn't matter. They're the same damn thing. These are the same thing. But here we go. I mean, I got it. It's done. The setup is now done. The bounds for y are the negative square root to the positive square root. While x goes from, can you tell me what x does?
0 to 2.
0 to 2. According to this picture. You need this picture. You see, we need this picture. You need the picture of the region. I mean, this picture was sort of helpful, but I really need the picture of the region. All right, yeah, I mean, I helped you. Do I have to do any more? No? Okay, good. Hang on, what would you do if you wanted to keep going? Integrate with respect to y? Oh, well, hang on. First, you should clean up a little bit. Those 4's are going to cancel. You'd have a better looking, you'd have a little negative x squared, negative y squared, positive 2x. And that's what you're integrating right here, right, you guys? When you go ahead and subtract that. So then you integrate with respect to y, then you slap a y on there, y cubed over 3, 2xy, and then you got to plug all these nasty square roots into that y. Oh my God. Do they really expect me to do this? Let me see, what's their directions?
Set it up.
Oh, at the end of their question, they say, do not evaluate this integral. It could be hazardous to your health. That's what it says. No, I added the last bit. Yeah, they want us to set this baby up. Do not evaluate it. This would be horrible to evaluate.
Unless we had coordinates.
It would be cool in polar coordinates. It would be cool in polar coordinates.
But how do you do that when the center is shifted?
I know. All right. So,
Wouldn't it be r squared equals 2r cosine theta?
good. Let's talk just a little more about polar coordinates here a second. So, back to just a little review of polar coordinates. So, if you have r equals 2, you guys know what that is in polar coordinates?
Circle radius 2.
Good job. Circle of radius 2, centered at the origin. That's it, you know. Here's the thing, when you study polar coordinates back in chapter 10, there's all kinds of cool stuff. There's a whole category of stuff called limicons. They got a little cedilla, it's a French word with a little cedilla underneath that C. Limicons, and they come in this form. Here's one, 3 plus 3 cos theta. And you know, they're cool things. This particular one they call a cardioid. Looks like this. I mean, there's special polar shapes that we could study. Cardioids are interesting. There's such a thing as a cardioid microphone. I don't know what the hell it does. Maybe it maximizes surface area or something. Anyway, there's some engineering involved in some of these terms, I suppose. But that's a cardioid. Hey, look at this thing. 5 cosine 3 theta. That's a rose. They call it a rose. It looks a little more like a daisy. See that? It's this spiraling. These are special polar graphs from the world of polar coordinates that you could have or should have studied in chapter 10 a little bit. When you ease into our section 14.3, they try to remind you of these things. I really am not interested. I'm not interested in this. I'm taking 5 seconds to remind you. But I steer away from the cardioids and the roses, and I'm not trying to do those in Cal 3. I study them in Cal 2, but I'm not studying them today. So what do we need to know in polar coordinates? This one. And this one, which I didn't get to the other day. And that is, there's such a thing as an off-centered circle. So this one is the one I like. When it's an off-centered circle, and we just ran into it right now today. When you have an off-centered circle centered at A, radius A, which means you have a diameter 2A, then the equation for that is R equals 2A cos theta. And maybe we should kind of know that or know how to convert, but I'm not asking you to know all these limicons and cardioids and roses. I'm not. But I think I'm asking you definitely to know that, which is very basic, and off-centered circles like him. Are you with me? I'm kind of clear, right? I'm kind of a clear guy.
Why is it not
Here's another one. If you had one off-centered here, A and 2A, his name is R equals 2A sine theta. It's kind of a theme in polar coordinates. If it kind of lives on the y-axis, it uses a sine function. If it lives on the x-axis, it uses a cosine function. It's kind of a theme in a lot of polar coordinate graphs. What What did you try to ask me?
I was wondering why it wasn't r squared, because over here we have x squared and y squared.
Yeah, I know. Well, so let's do what you did. You were getting there when you said a few minutes ago, you said, okay, if I want to know what he is in polar coordinates, perhaps I should convert him. And by the way, I'd like to convert him from here, not this mess. So if I want to convert him, you said x squared plus y squared is r squared. And you're right. And then x is 2r cos theta. And then when so boom, bam, bing, he's converted. We converted him. Okay? And
Divide by r.
and if you divide by, because we like to solve for r, and the best way to solve for r would be to divide by r right here. And if you divide by r right here, you have discovered the equation for, this is the polar equation for this thing we were talking about.
Okay.
But I just introduced it as its own thing.
And in our case, a was just 1.
That's right. In our case, a was
That's
1.
where it went. Okay.
That's true. But in general, I am trying to call your attention to these off-centered circles. We might need them for polar coordinates. That's it, though. I think I'm trying to call your attention to this. I'm not really going to be I'm not going to get. All right, that's enough. We got enough to convert the polar coordinates. So we're going to integrate over a region. Hopefully our region is circular. If our region looks like a damn cardioid, I mean, I don't really want to do it. And my problems, I don't think I assigned anything like that. Hey, so now after that little review of polar coordinates, where was our problem? This is our problem. Maybe we could convert this thing into polar coordinates.
All right, let's do cos theta.
I mean, see, it's after you set up the integral, it's maybe, well, whatever. You can set up the integral thinking in polar coordinates, or you can set it up in rectangular coordinates and then convert to polar coordinates. But here I go. I'm going to try it. Now, my integrand was this, okay, but we subtracted it and got this. So here's my integrand. Now, can you help me convert that to polar coordinates?
R equals 2 cos theta.
I mean, my integrand right here, I would call that, if you factor out the negative sign,
Negative r squared.
it's a negative r squared. That's a negative r squared
Okay.
plus 2x. And what's x? R cos theta. So that's this integrand converted. That's pretty easy, you guys. But you got to know a couple formulas. Hey, what about the dy dx?
R d r d theta.
Good job. R d theta. That's right. That's we just converted that. And now we got to convert our bounds. But again, listen to me. You don't really convert the bounds by plugging crap in. The way you change bounds is rethink the integration of the region. And the region is right here. And the name of this, it did have these nasty square root names on that region. Now it has this name. The name of this circle is r equals 2 cos theta. And r, y moves up and down, x moves left and right, but r moves from the pole out.
0 to 1.
So r goes from 0 out to whatever it hits. And what it hits is, and what I do is I draw several of them because I guess I'm sort of trying to draw an arbitrary r stick that goes from the origin out. And anyway, it goes out and it hits this curve. And what's the name of that curve?
0 to 2 cos theta.
2 cos theta. So the bounds are what you just said. R goes from 0 to 2 cos theta. That's the name of that curve in polar coordinates. All right, hey, last thing I need. I just need some bounds for theta. I just need, while R is doing that, a certain amount of theta will map out this circle.
0 to pi.
And you might think 0 to 2 pi, it kind of seems like you should do 0 to 2 pi, and it's wrong. 0 to 2 pi would be going around twice. I'm sorry, let's see. I don't know how to explain this other than to just tell you. These circles that sit off on the side, They only need theta from 0 to pi to map it out. That's all they need to map it out. Let me just explain something. If you've made a chart and started plotting points, that's how you really see this. What you would do is you would plug in a 0 for theta, you get this point. Plug in, 10 degrees, you get, 20 degrees, 45, you know what I mean? 60 degrees, right? Are you following me? 90 degrees, I think you would get this point. Then you come over here and you try to do 91 degrees or 120 degrees, and guess what you'd get? You'd get some negative r's. You'd be getting this r, and this r, and this r. And by the time you plotted pi, you'd be getting this r, and you did this whole circle from 0 to pi. Did that make sense? If you were watching me, it made sense. And you just kind of got to make a chart and do it if you really want to understand it, or you can just believe me. These circles don't require 2 pi, they just require 0 to pi. So that's what I'm going to put, 0 to pi. The truth is, any interval of pi would work. I'm going to say this. I could put negative pi over 2 to pi over 2. And maybe that's a little more instinctual for this one. For this one, you might think negative pi over 2 to pi over 2. You might think that, but the truth is 0 to pi works also. Or pi to 2 pi works. I mean, any interval of pi kind of works. We did it. We converted to polar. That's good stuff, you guys. This was 33 and 14 too. I wasn't supposed to convert it to polar, and I really wasn't supposed to evaluate it, but it was a good example. I'm trying to teach you both things. I use these 14.2 problems to show you the beauty of 14.3, switching to polar. When you go to 14.3, they tell you to switch to polar all the time. That's what you're doing, and it's good stuff. We weren't supposed to do this one, and perhaps we could. I maybe don't really want to. Maybe I don't want to. But well, I could let you go early since it's spring break.
Sounds good to me.
Students never argue too much about that. I don't ever get much of an argument. All right, well, let's quit.